Hey everybody, welcome back. This is Ryan Linfield and you're joining me in session 7, part 1 of the IC&D2 course. When we left off yesterday, we were talking about VPNs being utilized to create tunnels from one point to another. It seems like anytime I talk to an engineer and I talk about VPN tunnels, no one bats an eye, no one flinches, it's just a VPN. But when I talk about GRE tunnels, everybody gets quiet. And GRE's really not any different. Anytime we talk about tunneling, it's just encapsulation. So some data comes into the router, we take that data, we put it inside of a new box, and we ship it somewhere. That's all it is. Whenever you use IPsec, it's very similar to GRE. IPsec has encryption, and it has integrity, and it has authentication, which GRE is missing. But it's basically doing the same thing. It's taking some information from a user, throwing it inside of a box, carrying the box maybe across the internet or across any type of network, and then when it reaches the destination, they take the box, they open it, and they send the original data. So basically just encapsulation. GRE does, I guess you could say, the same thing as VPN, but it does it without encryption. And you go, well, why wouldn't you just use a VPN? Well, IPsec doesn't support multicast, doesn't support broadcast, and only supports IP traffic. And you go, okay, well, IP traffic, not that big a deal. Well, it depends. Sometimes we want to do different things across a network, and GRE makes it possible. So anytime you dream up a scenario where someone says, nope, you can't ever do that, it's not possible, GRE is what you would look to and say, could I use GRE to leverage this capability to maybe give me the results that I'm after? So I'll show you a little bit of a story how GRE saved the day for me one time. Prevented me from shipping a lot of equipment overseas, which would have taken forever. And I think once you kind of appreciate GRE, you'll be a little bit more interested in learning it. So let's go ahead and take a look at it. I would say that GRE could be utilized for packet stunts. What is a packet stunt? It's just doing weird things with your traffic that maybe not, might be a little bit unconventional. So we specified GRE is just generic router encapsulation. It's a simple box. That's what I'd like for you to think of it as. And we open that box, and I'm not a very good artist. But you get the idea. We've got our box here, there's our box lid, and we're just gonna put data in there, and the router is gonna get our data from one point to another. The difference, once again, beyond IPsec, is that this can carry non-IP data, it can carry multicast, and it can carry broadcast. So sometimes what you'll see companies doing is actually using GRE inside of IPsec, and it allows them to put non-IP, multicast, or broadcast traffic across an IPsec VPN. So let me show you a scenario where GRE once upon a time saved the day, and that's going to take place in Tampa, Florida, circa maybe like 2009. And we had a customer, the company that I was working for at the time, had a customer that was based in London in the United Kingdom. And I was supposed to go do a class in London. This class was going to be for CCSP, or CCNP security as it's now called, and I was going to do a 2-week boot camp. Within that boot camp, one of the labs that we did on a firewall used a technology they call transparent firewall. And a transparent firewall is where you'd actually take a firewall, like a Cisco ASA, and you'd put it in the middle of a VLAN. So the network on the left is 192.168.1.0, just for example, and the network on the right is 192.168.1.0. This is not what we typically see a firewall doing. Normally there's a different subnet on each side, and we're routing between it. Well, in transparent mode, this is basically a layer 2 device. It's acting as a bridge, forwarding based on MAC addresses, and as MAC addresses go back and forth, we're able to filter all the way up to layer 7. So I can build policies based on HTTP, or FTP, or SIP, or whatever protocol it is that I want to inspect, but as far as the firewall, it's operating as a layer 2 bridge. Is everybody okay with me so far? Keeping up? I hope so. All right, so what happens is we've got this rack of equipment in Tampa, Florida, where I've got ASAs for each of the students. And the tricky thing is behind the ASA in one of the labs, you'd have a server at, let's say, 10 dot the pod number. So my pods would be like students 1 through 8, dot 1 dot 100. And basically I had 8 servers and 8 pods. And then I had my students in England that were at 10 dot p dot 1 dot, let's say, 20. So basically I've got a subnet in London, I've got a subnet in Tampa, Florida, and what I need to have the students do is to be able to configure the firewall so it can permit some protocols and deny others, even though the students are in London and I am and the equipment is in Tampa, Florida. I'm also in London. I just didn't want to bring all this equipment with me. So what we do is we bring each of these interfaces into a switch. So this is just a Cisco Catalyst switch. And let's just say it was a 2950, because that would have done the job. From this 2950, I do a trunk to a router. So far, so good? This is a trunk link, so it carries all the VLANs that go to all the ASAs. That's the ASA, which connects to each pod server. You see 3, I guess 4, but there's actually 8. So server, 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 and each of these is an ASA. This is a switch. This is just a regular old iOS router. Everybody doing okay so far? And is everyone comfortable with the concept that we can trunk to a router? That's called a router on a stick. And that's how we actually talked about doing inter-VLAN routing. Back in ICND 1, we said if you want to route between VLANs, you could have a router with 2 interfaces, an interface in each VLAN. Or we could put one interface into the router, like one cable going into the router, and create sub-interfaces. Where there's sub-interfaces on the physical port, each sub-interface is in a different VLAN. That's what I did here. So it's router on a stick. You don't normally do router on a stick in production, except I did it here, and I do ASA on a stick in my house. So I've got many VLANs for lots of different types of testing, and then my ASA routes between all my VLANs. So it's not that weird to have a device that's basically what they call hairpinning, where traffic comes into the port and it comes right back out of it to do some routing function. So router on a stick isn't a new idea. It's just something you normally don't think about, but we did learn it in ICND 1. So we're going to build upon that a little bit. Routers can support something called a bridge virtual interface. If you've ever configured a wireless access point, you might have seen this before. It's where the wireless access point will have 2 interfaces, an Ethernet interface and a radio interface that speaks Wi-Fi. And a lot of times what you'll see on these is what's called a bridge virtual interface, and then you put your IP on the bridge virtual interface. This is a logical interface that you can reach through the radio or through Ethernet. So he's basically bridging between those 2 pieces of medium, kind of like a switch, but it's a 2-port switch with Ethernet on one side and a radio interface on the other. Is everybody okay with that so far? So if I want to manage my access point, I can get there through wireless or through wired. If you've ever set up an AP, you may have seen this before. Well, your routers are where BVIs originated. So what I did was I created different bridge virtual interfaces in each of my VLANs. And then I basically took the physical sub-interface and I bound it to a tunnel interface. And the tunnel interface, if you want to create one on a router, it's really easy. We just log into the router and we say interface tunnel 0. Let's log over here and I'll show you. I think I've still got GNS3 powered up. So we're goofing off with R6 and R9 yesterday. We could bring up R6. Let's see. Console to all devices. And to create a tunnel interface, from global config, you just say interface, tunnel, and you give it a number. I'm just going to say tunnel 0. I'll start counting there. And when you create a tunnel interface, it automatically, well, we'll give it a second. It should come up. And then once it does, you can put an IP address on it, just like normal. and you can manipulate it like it's a regular interface. So what is this tunnel interface really? Well, it's just a logical interface that's used for tunneling. So what I did was I said the tunnel source is the outside interface of the router in Tampa, and the destination was London. So what happens here, we've got a connection to this router in London, and the same thing is happening. This goes into a switch, and this is a trunk link. Behind this switch, I've got student PCs. Each student is in a different VLAN, and I've got 8 students. This was just a solution that I came up with myself where I was able to use GRE tunnels. And then what I did, once I constructed that tunnel, was we now had a connection or a pipe from Tampa all the way to London. This is where GRE lives. And because I used a bridge virtual interface between a tunnel interface on one side and a fast Ethernet sub-interface on the other side, I was able to do bridging through GRE across the internet. So this is basically a layer 2 interconnect between 2 sites. Does that make sense? You don't have to follow all of the details, but if you get the big picture, you could appreciate that it's pretty awesome to connect 2 devices on the same subnet in 2 different geographic locations. This isn't something that you would typically do. It's just kind of a crazy scenario, and this is what I call packet stunts. I just think that's kind of a cool word. Anytime I would need to create something, if I couldn't do this, there was no way to get students on one subnet to talk to a layer 2 firewall that's located somewhere else. So if I couldn't satisfy this, I had to ship all this equipment to London, and then I had to ship it all back, which that would have been horrible. But here, I could have the students using their PCs traveling across a layer 2 tunnel. They're basically sending out an ARP. And when that ARP leaves their computer, it comes into the switch. It goes out across this trunk link, tagged. It hits a physical interface, which is bridged to a tunnel interface, which pushed it through GRE. So here goes my broadcast ARP traffic. It hits this side, it goes from the tunnel interface to the physical sub interface, and then goes out. So you could connect 2 locations at layer 2. Pretty wild. Another solution a buddy of mine used, and this wasn't that long ago, there's a toy company, pretty major toy company, and they had 2 big manufacturing centers. I think one of them was in Georgia or South Carolina. We'll say it's South Carolina. And the other one was in Massachusetts. So these systems that they had ran DECnet. They're mainframe computers, and they ran a very, very legacy protocol that we don't see anymore. DECnet is not supported across the internet, right? The internet is IP only. But they've got these legacy mainframes that this application is always run on that they still support. And they synchronize the 2 systems. So what they needed to have was a dedicated link for their WAN connection. Does that make sense? So this was a leased circuit from the service provider that cost several $100s every month. Using GRE, we could use the internet. So here's the internet over here, which is IPv4 only. Well, I put a router here, and this router can do IP, of course. And then you've got DECnet on the other side. So DECnet comes in, and we bundle our DECnet to a tunnel interface. It encapsulates DECnet traffic in an IP header, which we can use to get from router to router. Once it gets to the other router, we rip off the IP header, and we send out DECnet traffic. Now, once again, this isn't something that you're going to rent out and use tomorrow. Maybe you will. Maybe you see something and you had an epiphany and GRE is a solution. This is something that I use maybe once a year. But when I use it, everybody in the room goes, wow, that's awesome. I can't believe we pulled that off. And that's what it really is to me. It's kind of like duct tape. It's extra encapsulation, so it's not beautiful. And typically there's a better solution. Like for layer 2 interconnects, you might have something like MPLS. But an MPLS, which is multi-protocol label switching, if you want to get an MPLS circuit set up, it's going to be, hundreds to thousands of dollars a month. You have to get it set up with the service provider. It could take, months to get provisioned. With GRE, all I needed was 2 routers and time to configure it. So I could set up a GRE tunnel and do a layer 2 data interconnect or do a layer 2 non-IP. I could move any type of layer 3 traffic across the internet using GRE. All I need is IP connectivity between the 2 sites, which internet access gives us, and then GRE to use as tunneling. So does everybody get a pretty good idea of what this is? If you've ever been to Target before, and you've seen the big, or Walmart or Home Depot, you've seen those big storage bins. What can you put in them? Christmas lights, old clothing, pots and pans, books, doesn't matter. That's what GRE is. It's just a box that anything can go in, which sounds insignificant until you realize that most other protocols that we work with have a lot of rules and exceptions to what they're allowed to carry, where GRE doesn't care. He goes, we're just a box, we carry anything, and we can move it across IP. So these are some pretty unique scenarios, but they are real-world scenarios. These are things that I've done and friends have done. My buddy with using it across DECnet, that was pretty recent. Unfortunately, you'd think all the DECnet would be gone. But it's just like an extra card that you can play if you really need to. It's like the Swiss Army knife of networking. So without any further ado, let's look at the actual courseware. And I think you'll find the courseware to be a lot easier to follow than my story probably was. But the courseware doesn't really give us any practical application. So that's why I gave you the stories. So GRE stands for Generic Routing Encapsulation. It's one of many tunneling protocols that exist, and it's IP protocol number 47. What does that mean? Well, when we look in the IP header, I say all our headers are like envelopes. They've got source and they've got destination, and with an IP header, it would have IP addresses. There's also a field in here called IP protocol. I've pointed this out a few times. I try to get people aware of this in ICND1, and I don't stop hammering it. If you come to my security classes, I'm telling guys to look at it as well. This is what we see in the IP header that says, I'm carrying this at layer 4. For example, if it says IP protocol equals 17, well, that's going to be a UDP header. If IP protocol equals 1, that's an ICMP header. If it equals 2, it's IGMP for signaling multicast. If it's 51, that's an ESP header. This is what an IPsec VPN uses. So all they're saying here is 47 equals GRE. If you were to look inside the IP header, it would have a 47, and if so, this would be GRE. What's inside of this? It could be more IP addresses, it could be more TCP headers, it could literally be whatever you want. This allows routing information to be passed between connected networks. Now, what they did here was they just made a huge jump in the storyline. So GRE, I said before, it's kind of like duct tape. It lets us do packet stunts when you're trying to form a solution and there's a bullet point in the protocol when you're reading about it that says this is not supported. Well, that's where we go back and we pull GRE into the mix. So for example, if I had local site, so this is headquarters, over here is the branch, and my branch office, they keep putting up new VLANs and rolling out new subnets, and every time they do it, I have to create new static routes on my router that point to the branch. That's ridiculous. We have an IPsec tunnel between us and the branch, and I would love to run a routing protocol across IPsec, but IPsec says no multicast and no broadcast. How is that going to affect my routing protocols? Anybody? Is broadcast important for routing protocols? Not really, right? It was only used in RIP version 1, which we don't see. But multicast, let's see. RIP version 2, EIGRP, OSPF. If you're doing anything besides BGP, which is not what you use inside of a company. That's what you use outside of a company. If you're using an interior gateway protocol, these guys discover one another by sending multicasts. If IPsec doesn't support multicasts, how do I make router A and router B form an adjacency? And there are other hacks that you can do to make this work, but GRE is one of the most commonly used. What we can do is create a tunnel interface on each side, and then we form an IPsec tunnel between them. So basically, the data comes in, it gets encapsulated with GRE, and then it gets encapsulated inside of IPsec. The GRE gives us the ability to support multicast. The IPsec will carry GRE because it's from router A to router B. It's a unicast, and it also gives us some privacy. Is everybody following all this? Notice on the left, they say passenger protocol. On the right, they say passenger protocol. In the middle, they say transport protocol. That's because GRE works in the middle, and you can put whatever you want at the edges. Could be DECnet. Could be AppleTalk. Could be IPX. It could be crazy legacy stuff. But the deal is, with GRE, it really doesn't matter. We can carry whatever we want through a GRE tunnel and use GRE as a transport. Cool. So that's GRE from a high level. In order to implement GRE, we're going to create tunnel interfaces. We got to put IP addresses on those tunnel interfaces. We have to tell the router how to get to the other tunnel interface. And then we'll specify the GRE tunnel mode. So when you create a tunnel interface, let's pop back over here. You can say tunnel mode. And there's different types of tunnels that you can create. There's MPLS, there's GRE, there's IPsec tunnels, there's IP and IP, there's IPv6 over IPv4. So there's different types of tunnels that you can build. Now, here's the other thing. If you're looking at this going, oh my gosh, there's so much, I've spent literally thousands of hours in labs dreaming up weird scenarios, reading books, trying things out. I've never in my life touched these 4 protocols. Never needed to. I've never touched AppleTalk. You know, I was using IP back when AppleTalk was an option. I was using IP when IPX was an option. I've never used NOS or RBSC. So if you look at a list, don't ever feel like, oh my gosh, there's so much I don't know. I can hit question mark on any device, and I swear I see commands I've never seen before, and I've been doing this my whole life. There are some things that I've done 100 times. There's some things that I've done never. So just don't let all the options scare you off. The tunnel mode is GRE by default. So we don't have to change it. When you create a tunnel interface, it's going to do GRE. But one of the other things that we create these tunnel interfaces for is doing IP6, IP version 6 over IP version 4. If you wanted to do that, that's another thing tunnel interfaces could be used for. So let's say that, you know, here's the internet, and in this location, we've got Verizon. Over in this location, we've got Comcast. This is just the internet. Unfortunately, our internet connections in both locations are IP version 4 only. So when we look at our routers, what you do is you have version 4 on this side that faces the public internet. On the inside, we're going to run dual stack, which means you've got version 4 and you've got version 6. Whenever version 6 traffic comes in, we're going to send that to a tunnel interface. The tunnel interface is a point-to-point connection between those 2 routers. So your IPv6 traffic comes in. Here's our layer 5 through 7. Here's a TCP header. Here's an IPv6 header. What are we going to do with it? We're going to put it inside of a v4 header and send it across the internet. When it gets here, they rip off the version 4 header, and into this network, we send the original stack. This would be TCP, and this would be IP version 4. I'm sorry, IP version 6. Does that make sense? So what I did here was I still created a tunnel interface. and I said, I want to create a point-to-point tunnel between my router and that router. And whenever traffic comes into the tunnel interface, we encapsulate it. Normally, we would say, we don't even have to say it, but normally the mode is going to be GRE. If I say IP6 over IP, it doesn't need a GRE header. It just puts two layer 3 headers in a row, a version 6 header and a version 4 header. So here's version 6, here's version 4. Both of these guys are layer 3. It gets routed across the internet. We've stripped the first layer 3 header, and now I can do an IP version 6 ping between my two offices, even though I'm using the internet as a transport. That's just another example of tunneling. Is this going too slow? Is this a good pace? I just want to make sure everybody can wrap their minds around this and get as comfortable as you can from looking at a whiteboard. I know for me, I would have to set it up and try it. But this is really, really important stuff to understand. This is basically what your VPNs do. And as you get to the more advanced classes for VPNs, you'll start talking about using GRE inside of IPsec and building full mesh solutions between all your sites with it. So most of the time, like I teach ICND2 to you guys from 5 to 7, and I'm doing a VPN course from, from 2 to 4. So we're going over something called Dynamic Multipoint VPN, which uses GRE, and it's multi-point GRE. So it starts to get pretty hairy pretty fast. And I've got many times when I teach that, none of the audience has used GRE before. So it's an important protocol. It's used behind the scenes of a lot of other protocols. So DMVPN uses it. Some of the data center interconnects that you learn about in like a Nexus 7000 class, if you go into like the data center track, they would expect you know about GRE. When you go into the security track, they expect that you know GRE, but it was never really brought up before. So I'm excited to see that it's in the new ICND, but just running through the slides isn't always enough, so I'm going a little bit slower. If this gets to be obnoxiously slow at any point, let me know, and I'll pick up the pace. So we're just tunneling. We're taking packets, putting them inside of other packets, and routing them. And when I say packets, I'm referring to a layer 3 datagram. All right, so this is one of the things that we can do. Whenever we create a tunnel, you specify the tunnel source and the tunnel destination. Typically, the source is your outside interface, and the destination is the far end interface. So let's take a look at what this may look like. We've got the branch on the left, and we've got headquarters on the right. We say interface tunnel 0, and then they're saying tunnel mode GRE for IP encapsulation. Now, that's the default mode, so I'm not sure that you'd have to type that, but it wouldn't hurt. The next thing we're doing is giving the tunnel an IP address, 192.168.2.1, and over here, this guy's at 192.168.2.2. So they're on a common /24 subnet, right? That's for our tunnel interfaces. But to communicate, to go through the tunnel, we're going to go ahead and encapsulate this IP header inside of GRE. This is layer 3, this is layer 4. We got a lot of encapsulation. Now we do a new layer 3 header, and the source should be our public interface, and our destination should be the remote site. Everybody follow that okay? These are going to be public IPs if you're using the internet. The source is our site, the destination is their site. And all we're doing is defining what the new IP header is going to look like. Thanks for the thumbs up. Lets me know everybody's on track. So on the headquarters side, how much different is it going to look? Not at all. We give it a different IP because this guy's .2, and we say that our public IP is the source, and their public IP is the destination. That's not scary at all, is it? The concept is sketchy because so much of this is intangible, but it's really not too bad to set up. So let's go ahead and let's just try to do this. Let's take a look at it. We'll come over to our routers, and I've got R6, and I'll say my tunnel will have an IP address of, and I'll do the same IP as 192.168.2.1 over here. And on the other router, which is R9, I'm going to use 2.2. Oops. See if we can set these up side by side. All right, R6 and R9. So I'll come over here and I'll set up my tunnel interface. Come on, conf t. Interface tunnel 0, IP address 192.168.2.2. And it needs a subnet mask. Cool. Now at this point, I can do a do show IP interface brief. And a little bit ugly to read, but the serial interface 10.10.69.9, I want to use that as my source. So I'd say tunnel source 192.168, nope, tunnel source 10.10.69.9. Tunnel destination 10.10.69.6. That's going to be router 6. And on this side, I just flipped that. And now it changed state to up. Now, I haven't configured the other side, so that's one of the super sketchy things about GRE. You just saw that I configured one side of the tunnel. The other side isn't configured yet. He doesn't know that that's the destination. But regardless, your router goes ahead and says, you're good, the tunnel's up. So you can't really trust a tunnel interface when it says that it's up and up. Just FYI. Wasted some time on that before because I actually believed it. Coming over here to R6, if I say, ooh, this super putty utility really doesn't like being in the breakout tabs. Let me put this back. There we go. And let's just move R6 down here by R9. So on R6, I'm going to do the same thing, do show IP interface brief. And there's my address. So again, the tunnel source would be 10.10.69.6. I'm imagining that this is the interface that I used to get across the WAN. And my tunnel destination is 10.10.69.9. And we give it a second, that tunnel interface should come up. So show IP interface brief. Let's make this a little bigger so it formats nice. There we go. Notice that I have a tunnel interface just like a regular interface. Notice additionally, I have no other way to reach 192.168.2.2. There's only 2 IP addresses configured on this router. If we look at our topology here, you see that this has connectivity this other way. But those interfaces are not configured. This is our only good link. So let's keep going. If I ping 192.168.2.2, it works. Cool, right? Because I'm 2.1. If I do a show IP route, we'll see that 192.168.2.0 is connected on the interface called tunnel 0. Should the IP address be a /30, that would be much better practice. Absolutely. Let's fix that. Interface tunnel 0. 192.168 2.1. Let's actually tell it that this is the IP address. And then we'll do 255, 255, 255, 252. And that would be much cleaner. There we go. So we've got 2.1 and 2.2. So far, so good. Let's go ahead and sniff that and see what's going on. Minimize that. Bring up this. And we've got this serial link. We already said we're going to capture on it. So let's just start Wireshark and see what we see. Let's delete this capture. And let's just start it fresh. I believe the encapsulation's PPP. If we say do show interface 000, here we can see that the encapsulation is point-to-point protocol. So when we come back here, I can say sniff this link, and the encapsulation is going to be PPP. Now I can start Wireshark, and we can bring up PuTTY, and we can do some pings again. So, all right, and it's still working. So we'll pop back over here. We'll go into Wireshark, and there's our ICMP messages. But I know that earlier you guys saw me drawing out the header diagrams. Like it's layer 3, and then it's layer 4, and then it's layer 3. And you're like, are you serious? Does it really go like that? Well, don't ever believe anything that you read or anything that anybody says. Okay, well, don't be that skeptical. But if you see anything and it doesn't sound right, that's a perfect point to break out Wireshark. Don't Google it, because whatever you want to believe, you can probably find somebody that says that on the internet, right? But you can definitely validate it inside of Wireshark, because packets never lie. That's what we're going to do here. We're going to take a look at what's going on with the encapsulation of those pings. We'll stop the capture for now, look at our ICMP echo request, and we see here we've got 192.168.2.1 pinging 192.168.2.2. How cool is that Wireshark showed us the internal IPs? Can you see what's happening here? We've got our layer 2 header, which is point-to-point protocol. Now we've got a layer 3 header going from 10.10.69.6, which is R6, headed to 10.10.69.9. Here, we've got a GRE header. It's real simple. It just says what I've got inside is going to be IP. That's it. It looks kind of like a PPP header. He says, I'm carrying IP version 4. GRE says, I'm carrying IP version 4 too. It's just a real simple header. And then if we look at the next header, this is what's actually inside. 192.168.2.1 talking to 2.2. So we've got these two layer 3 headers here. Wireshark is showing us the internal one. These are the guys that are actually doing the ICMP echo request. How cool is that? Is everybody into this? Or not so much? If I'm the only one that's excited, let me know. But I think this is pretty cool stuff. You couldn't always just do a Wireshark, do packet captures, this easily and show people the data structure. So that's what GRE is actually doing for us. All right. That's probably enough for now. Let's just pop back into the slide and kind of step through this. So we saw that it's not hard to build. We set the source and destination, which based on your perspective being HQ, that's the source, whatever interface you're going to use to build the tunnel typically, and the destination is the receiving router. If you want to verify the configuration, here we see it's tunnel 0, and here's the IP address. I said before, don't really trust this. We saw that the tunnel wasn't actually up, but it told us it was up and up. The things we do want to verify are the IP of the tunnel and the tunnel source and destination. So again, this is us, this is the other guy. Their configuration should be exactly reversed. Like I said, when you do a show IP route, this is where you see things going into the tunnel. So one of the things I could do, just if I wanted to get a little bit fancier, is I could come over here, pop back into our routers, and on R9, let's just take a look at our routing protocol, show IP protocols. And I've got no routing running between R6 and R9. That's okay though. I can look at my other interfaces here, and I'll make this network 49 off of R9. So show IP in brief, and we can say conft int fa0/0 IP address 10.10. Make sure that's the right interface. So this is my F00 interface coming down here to F01 on R4. So we'll go to FA00, IP address 10.10.49.9. Make sure it's not shut. And the link change its state to up. Cool. So now what we can do is come over here to R6, and say conf t IP route, and we'll just create a static route. The 10.10.49.0/24 network is going to be reachable. And normally what I tell everyone to do is put a IP address of the next hop router. That's what you should do when facing the internet. But what we're going to do is actually put a tunnel interface as the next hop. So I say if you want to get to the 10.10.49 network, go to tunnel 0. And then what we should be able to do, knock on wood, is going to be ping 10.10.49.9. And that works just fine. Is that pretty cool? Does everybody see that in what scenario is GRE used? Did you miss the first 10 minutes of dialogue? Were you not listening? GRE is our duct tape anytime we want to get something from point A to point B where they tell us it won't work. I gave a scenario where I was bridging. I connected 2 VLANs, one in London to one in Tampa. It was the same subnet space. They told me that I had to bring a rack, literally a full cabinet of equipment with me to teach the class. I didn't want to do it, so I was able to connect students on one subnet to the exact same subnet in Tampa and demo transparent firewalls. You could use tunneling like this if you wanted to do IPv6 across IPv4. So imagine that you have 2 offices, headquarters and branch, and you want to start rolling out IPv6. But your internet service provider doesn't do v6. How do you connect the offices together? We do v6 inside of v4, or you could do v6 over GRE. So we can do this anytime you're trying to make something work and it doesn't work. At least for me, GRE is the duct tape that I can get out to bend all the rules and pull off various packet stunts. The scenarios that I showed you today are going to seem a little bit out there. And like I said, this isn't something that you're going to run out and use immediately, but advanced topics that you'll learn in the data center classes and the security classes assume that you get GRE. And what you should know about GRE is that it's just an encapsulation type. It's just an empty box that we can put anything into and get it anywhere across an IP network. Sounds kind of like, big deal, but it's a huge deal because IPv4 connects all of us globally. And without GRE, if you wanted anything that was an IP to talk across the internet, it wasn't possible. But with GRE, it is possible. So hope that made sense. I went into a lot of detail at the beginning of the session. So if you just watch the recording of today's session, at the beginning I tell some stories. Cool. And here we're showing, again, that the IP routing table, show IP route, says if I want to get to the 10.10.49 network, anything that's destined for 10.10.49, just send it to tunnel 0. What's going on with tunnel 0? Well, it just encapsulates it in GRE. The GRE is going to go inside of IP. The IP is sourced from here, destined for there. That's it. And yeah, normally you'll use it across the internet. If we want to connect 2 sites using crazy protocols that somebody doesn't want to support, we can do that with GRE. All right, coming back to our slideshow. All right, that was it. So GRE is a tunneling protocol that can encapsulate a wide variety of protocol types inside of IP packets. So basically, we can do anything, I say that loosely, but almost anything over IP. One of the things that made this cool, as I explained earlier, was that IPsec is what we normally use if we build a VPN between 2 sites. IPsec is IP only, doesn't support multicast, doesn't support broadcast. So if you have an application in your environment that needs multicast or broadcast to work between 2 sites, they go up, your multicast application just won't work because IPsec doesn't do multicast. So you have to go buy a dedicated link. And like I said, a T1 might cost you $700 a month just to get whatever application it is to work across, from site to site. Well, the T1 at $700 a month is 1.5 megabits per second. Your broadband internet connection, maybe let's say it's $300 per month, and $300 in Tampa, Florida, that would get me a 500 megabit per second internet connection. We've got cheap, fast internet, but you get the idea here. These are the customers that I'm dealing with. And they might not be connecting to another office, they might be connecting to a data center. And that data center could have gig or 10 gig. So now I can use this blazing fast connection and I can make a multicast or broadcast work across it. And I can also make non-IP traffic work across it. Because what I would do is I would put GRE inside of IPsec. This gives me the ability for non-IP traffic, multicast, broadcast, and it gives me confidentiality, integrity, and authentication. So it does it all securely over an inexpensive connection that you already have and want. And maybe it gives you more budget. If I can get rid of this, I can say, can we go to a gig now? And that's probably how I'd have to pitch it. Or I'd never get the gig upgrade. I'd say, if we bump this up to a gig, I could kill that other connection off. And they go, did we really need to kill it? Do we really need the gig? And I go, no, not really. You probably need 8 megabits, but it wouldn't hurt. Like just trying to reappropriate some of those funds. What else? You must contain a tunnel source and a tunnel destination. And you should verify that the tunnel is up after configuring it. I would ignore that because even if the tunnel's down, it's still going to work. So it'll still show that it's up. Let me test that. We'll come over here. I'll go to R6, config T, int 00/0. And let me just say no IP address. No IP add. So my physical interface is up. We're still doing PPP. So on this side, I should say show interface 000. It's up and up, right? Can I ping 10.10.69.6? Definitely not. There's no IP address on the interface. But if I do show IP interface brief, we should see that tunnel 0 is still up and up. When there's no way that this tunnel, if you think about it in like a logical sense, our tunnel isn't really up. We don't have connectivity because this side doesn't have an IP address. The minute I give it an IP address, and this side as well, do show IP int brief, he doesn't even have an IP address. But he's still, oh, right here, see, our tunnel on this side is up down. So he's not happy. If I come back into 000, see that this side says up down, but the other side says up up. All you're really seeing in the up up on your tunnel interface is relative to your local configuration. If the other side is screwed up, you don't get much info. If I say, let me just go back to my history. Here we go. Uh-oh. Oh, no, that was for the tunnel interface. All right, so I just need to type it from scratch. IP address 10.10.69.6. And this should have been a /30 as well, because it's just point-to-point serial. And we should come up. And there we go. Now, since our physical interface came up with the correct IP address, we now see the line protocol and tunnel interface 0 is up. I think that is due to when we do a show run int ton 0, he's expecting to source packets from 10.10.69.6. So if that address isn't around, I think that's why we're getting the down down. And as soon as it comes back, it makes the tunnel interface happy. Because our physical interface, when you see up and up, this is layer 1 and 2. So this being down had to do with this IP address, I would wager. And if we do show IP int brief, we now see everything is up and up. Cool. How is that for the first 50 minutes of class? Pretty cool stuff. Not the most practical, but still I think pretty exciting. And this is kind of the, I don't want to say hacker stuff, but it really is. You can hack together a pretty clever solution. You're sitting at a table, everybody's trying to solve this problem and it can't work, and you'll maybe remember this. You'll be like, wait a minute, could GRE fix it? You get quiet, you start Googling, and you go, I think we can do it with the GRE tunnel. And voila, you saved the day. At least that's what I hope will happen. Let's go ahead and take our 15-minute break, And when we come back, we'll start our final module, which is on network management. We'll do a little bit today, a little bit tomorrow in 2 chunks, but we don't have a ton left. So the rest of the stuff that I'm going to show you, I think is pretty easy. Information about licensing, syslog, SNMP, all pretty basic. So look forward to seeing you guys in 15 minutes, and we'll start the final chapter.